So currently we'll be presenting MojiMi. So currently in technology there are several trends, one being social media. So with social media rising, social media apps such as Snapchat introducing filters becoming ever more popular, with other social media sites such as Facebook, Instagram, TikTok also implementing them. Another trend, of course, is anonymity. With the rise of technology, we want to stay as anonymous as possible. And this motivates the introduction of MojiMi, which takes an input image. We want to do face detection on the image to detect faces and post the corresponding emoji to such faces onto the image. So with these, we detect emotions: happy, neutral, sad, angry, and surprised, which isn't listed there. So how we do this is we first receive an input image, just like an image from Instagram, if you will, unspecified, with or without people. We want to perform face detection with Azure Face API, which does the bounding box for us. We get the crop picture, resize it to 64 by 64. Then we put that into our eCNN, which is the model we'll be talking about today. And as a result, we get our output image with the emojis on such faces.
Yeah, so we first start with a baseline model of two fully connected layers, which result in test accuracy of around 70%. On top of that, we build our eCNN model, which consists of two CNN layers and two fully connected layers. For each CNN layer, it's followed by a max pooling and a rel activation. For the first rel layer, it's also followed by a rel activation. And then it is trained with Atom Optimizer and the cross entropy loss, and then reaching a test accuracy around 75%.
So with the dataset to actually train this, we first applied Flickr Faces High Quality, which is 70,000 images scraped from Flickr, and they're all high quality images. They're images of people in the wild. Now, because these images are mainly happy and neutral, we needed to introduce more. And as a result, we used AffectNet, which is 420,000 images, this time labeled by a professor and his team. And they're all in the wild, and they're in different orientations, as you can see some examples up there. And to actually form a data set, we use 30% Flickr and 70% AffectNet to actually make the whole data set.
Yeah, so for our data process, we first start with our Flickr dataset. So after passing that to Azure, we crop and resize it to 64 and 64. And then realizing there's a huge gap exists between happy, neutral, and the other three categories, we perform data augmentations, and then later on we will normalize them to a range of 0 and 1, and then passing to our model as the input. However, realizing that after augmentation, there still exists a gap between the number of images of happy, neutral, and the other three. We introduced AffectNet as mentioned before. And here's the distribution of how our final data set looks like in terms of emotion categories. So here are our training curves. It took us around an hour to train the 30 epochs, and then we obtained the best model parameters at epoch 15, using early stopping. And then for which result in the model has test accuracy of 74%. So here's our confusion matrix. As you can see here, the model performed the best for the happy and neutral, and it gets slightly confused about sad, surprised, and angry.
So with the results now actually taking this, so this is actually the example picture, and this is the first test that we did with it. So given a picture from Instagram, it's actually able to crop it, so we're able to resize and crop it, give probabilities based on the emotions detected, and put it on a corresponding image. Now let's explore the other different images possible. So there's some limitations, of course. Since we use Azure, face angles is a limitation. So since Azure cannot detect face angles that well, side faces, we cannot detect, and we cannot perform emotion recognition on those. Another limitation would be face sizes or face fractions. So when you get a lot of people with, let's say, different face sizes or because of different angles, and if someone's covering someone's face, like this person right here, it also cannot detect that well. Now, of course, a big problem with us is emotional mix-ups. So as you can see, our model a little bit earlier was overfit. So for this example, you can see that all the emotion emojis here are either happy or neutral. And if you look closer, I guess this makes sense, because if you look at these two images, the one on the left, this one could be deemed as kind of angry, on the one on the other side is neutral. However, only slight features that identify, such as eyebrow angle, differentiates between the two. So for us, it could be easy to differentiate, but for a neural net, it may be a little more difficult. Similar goes for this for happy.
Yeah, so one of our main concerns is overfitting. As you can see, in our previous training curve, we actually overfit. And then we found one really time-efficient strategy approach is to use early stopping to get the best model parameters with the.
So with overfitting, there's also several strategies we try to implement. One being dropout, other one being L2 regularization, and reduce the number of parameters. So actually performing and actually trying to implement these three, we actually realized that the first two, dropout and L2 regularization, actually decreased accuracy and didn't improve overfitting at all. So for us, we just went with the third option of reduce the number of parameters, and hence we have a more simplistic model.
Yeah, and also we also try to use the transfer learning to decrease the training time. So we're passing our input images to a pre-trained model, and then based on the output of the pre-trained model, we train another set of neural net. So despite the time decreased significantly to 60 seconds, our accuracy actually dropped a lot, and we believe this is due to the overfitting, which is shown in the curve over here. And then we believe those overfitting and those issues are primarily related to the poor quality of data. Since we introduced the AffectNet, and then for the labels of AffectNet, we trust the people who previously labeled the dataset, which later we figured out it wasn't that accurate. And then also for the AffectNet, it also has a lot of variations. Like besides real human faces, it also have cartoon people's face, memes, and also the inconsistency between dataset is also a contributing factor to why the model isn't performing as expected. So for some future extension, we believe we can extend this to more like object detection as well, and also we can build our own face detection module. Thank you.
Well, that was a lot of content in 6 minutes. Well done.
Yes.
And also, it's amazing you seem to try a whole pile of things, including the regularization and the transfer learning. It's interesting that the transfer learning got you nowhere. Sometimes, maybe you tried too many things and didn't, but I think it's impressive that you did try those things. The only question I have is, you said one of the problems was the inconsistency between the two data sets, the Flickr and
yeah, because for the Flickr,
what do you mean by that? Yeah.
So for the Flickr dataset, because the quality is actually high quality.
You mean high quality?
High quality,
pictures?
like pictures, yeah. Sorry. And then for the AffectNet, the quality isn't as good, and also the way we process both are kind of different. Because for the AffectNet, we literally just took the original data set, and then for the Flickr, we actually pass it through the Azure API. So the way how they crop the faces may be slightly different. So
the cropping wasn't done by Azure in the second data set?
Yeah, so there were limitations with like the number of images, like the quota you get for Azure. So that was a big problem that limited us for that.
It's free, but only for a little while.
Yeah.
So only for a certain amount. Free. Yes. So good, interesting business model. Mike?
Happy to see limitations. It's always a good thing to include with ML models. Can you go to the transfer learning slide? The other side, sorry.
Oh.
So the output of VGG is a classifier. Were you just literally using its output classification as the input to your linear model? So that's why it didn't work. The feature you were trying to use that VGG was producing was just what it thought was the classification of the image. Because all your images were faces, what you wanted to do was cut out the final classification layers, use the feature layers that are produced by the convolutions.
I think we actually tried to do that. So we tried to, I think it's the 6th layer of the classifier. I think we also tried that, but then the accuracy was also around this. Yeah. So we just thought like if we do it this way, it actually trains faster. So we just put this model in here to like show it. And we feel like it might be because the data set is kind of noisy. So the VGG16 is too good that it pick up the noise so well. So like it overfits. Yeah.
That's a good point though. I didn't catch that. Any questions or comments? All right, thank you.